All right, guys and gals, we're back. We're looking at our last bit in functions, and what we're going to look at is a little bit different than what we've seen before. So we've talked about linear functions rather. We've talked about some nonlinear functions. We've looked at scatter plots. We've looked at lines of best fit. This last bit is completely different, and a lot of people like it because of one simple fact: we don't have to keep up with a lot of details. Right? The numbers bit gets thrown out the window, and we're drawing basically rough sketches. So let's talk about what is a qualitative graph, and we'll spend some time making them today. All right, so what is a qualitative graph? Well, it's real simple. These graphs are typically line graphs, and they don't have to be nice straight lines. Sometimes they involve curves too, but we'll try and draw lines for the most part, curves occasionally. And what they do is they represent essential changes in a situation. They typically do not have numbers on either the x or the y axis. So instead of us having to create a grid here and actually figuring out, well, what am I going to count by, and are all of my points just so, we can think of them as simply a rough sketch of the situation, right? We're just getting the essential changes, right? What is it basically going to look like, right? So here's some tips for when you're drawing. First, you got to know what each axis is measuring. So, and again, measuring, we'll kind of use that as a loose term, because we're not going to look at specific points. We're just going to get the gist of it down, right? I recommend that you read the situation at least twice, right? Once, just to get a general idea of what's happening, and then a second time to look very specifically for those important events, because that's going to tell us how our graph needs to change. And then finally, I recommend that you always use a pencil. That way you can make changes, because inevitably you'll make a mistake, and that's all right, but you want to be able to change those issues and make them correct. So you can use just a standard pencil if you want. I'm going to use a red pencil just because it'll show up a little bit better on the video, and I can still erase. So let's take a look at our situation. In this case, I just made something up for us to try. So here's our story. It says Mr. Lamar wanted to race his sons, right, which we do race from time to time. It says when the race began, Mr. Lamar started running faster and faster, which is a joke because I don't run fast anymore. And then it says, unfortunately, Mr. Lamar tripped over his shoelaces. That's a common occurrence. Fell and tumbled to a stop. All right, sketch a graph of Mr. Lamar's distance traveled over time. Now, notice how that's worded. Distance traveled over time. All right. The way these are worded is going to tell you what's going to go for the x and y axis. Remember back to slope. Slope, if you recall, one way to talk about it was dependent over independent. And notice that word I used, over. Dependent over independent. So when we see the way these are set up, it says distance traveled over time. This is telling us what needs to go on each axis. And notice that's one of the first things we need to know when making these graphs. What are we actually measuring? So on the x-axis, we're measuring time. Probably, if we're talking about a race, we're probably talking about it in terms of seconds. All right, this race is not a distance race. And then distance traveled. We probably don't have to get too specific on the distance traveled, but for the sake of argument, we'll go ahead and record it as feet. Because based on the situation, it doesn't sound like I got very far. All right, so that's our first reading. We have an idea. Mr. Lamar's taken time to race with his kids, ultimately fell. We're trying to keep up with how far did he go over the course of time. All right, so just how far did he go? So obviously, if we're down here at the origin at 0, 0, so to speak, no time has elapsed, so we haven't started the race yet, and 0 distance is traveled. All right, I haven't gone anywhere yet. All right. So let's reread it. This time we're reading it to look for those important events. All right. Now I'm going to switch out to a highlighter. That way we can highlight them. We're not mixing up reds with other reds. So here we go. It says, when the race began, Mr. Lamar started going faster and faster. All right. Now remember, if we're measuring distance over time, and let's draw on something here. If my line, for example, looks something like this, notice I'm not traveling very far, and I've gone a pretty good distance in terms of time. So that would be somebody going very, very slowly. This says I'm going faster and faster, so I'm picking up speed. So I might start, for example, maybe on a line like this, that says I got going faster and faster and faster. So notice this shows me going kind of slow. This is getting steeper. This is steeper still, showing I'm traveling a greater distance in the same period of time. Let's pretend that each one of these were a second. In this second of time, I've only traveled maybe half a box. In this second of time, maybe 3/4 of a box. In this second of time, notice I've traveled almost 2, maybe 3 boxes, right? So this is showing me speeding up. I'm going faster and faster, but notice I don't have an exact idea of how fast I'm going. We don't have the seconds marked, we don't have the distance marked, we're just showing that I am picking up that speed. So distance traveled, I'm going faster and faster and faster, and then let's talk about the next bit. It says, unfortunately, Mr. Lamar tripped over his shoelaces, fell, and tumbled to a stop. So something pretty abrupt happens. I'm going at breakneck speeds for someone my age, and then I trip and I fall. So what's going to happen to my distance? How much further am I actually going to go? Well, it says I tripped and I tumbled to a stop. That implies that I'm going to slow down. So my slope needs to start leveling off. So maybe I initially trip, I tumble a bit, I still tumble a bit, and then what's probably going to end up happening is I'm going to level off. Notice I've not traveled any further distance-wise. The time is still marching on, and I'm staying in roughly the same place, meaning I've come to a stop. Notice the distance hasn't changed. I'm not going up. I'm just maintaining. So this is one way we could draw this graph. Now, you could draw your graph differently, perhaps. Let me switch colors here. We'll use a pen this time. Maybe when you draw yours maybe is more of a curve up and then bam. Okay, but notice it's the same basic shape. You may not have a lot of those straight bits that mine has, but you're showing me speeding up. Oh, I tumble and trip and come to that stop. So again, we're looking for basic shape. We're not getting too hung up in the minute details. We're just trying to get those essential changes. Right? Let's try another one. Okay. Mr. Morse likes hiking, so he went to Natural Bridge State Park. He started in the parking lot well below the bridge. His hike took him gradually up a trail until he reached the bridge at the top of the hill about an hour later. After he took in the views for a few minutes, he decided to take the chairlift back down to the parking lot, which took 5 minutes. Sketch a graph of Mr. Morse's elevation over time. So again, notice our situation. We got to look at what we are measuring. Again, we use that term loosely because there's no numbers. In this case, we're asked to measure elevation over time. So elevation is going to go on the y-axis, time along the x. So let's do that up again. So time, maybe we'll say that's in minutes. Obviously an hour's passed, but we'll be all right. And then we'll say elevation, and I don't know, maybe we're still measuring in feet. That might be a decent measure. All right, so let's look at the situation. So we've read it first. We know he's climbing up, stays there a bit, and then very quickly comes back down. All right, but let's see if we can figure out what's actually going on. Now again, looking at this, if we're at 0, 0, that means no time has passed, and he's at his starting point. So in this case, he's in the parking lot. So if he were to travel up, he's going up the hill, and if he comes down, he's heading back down to that same level as the parking lot. So here we go. It says he starts in the parking lot. All right, so he starts there at ground level. He never does leave the ground, but obviously we'll say that parking lot level. And he took the trail, and it went gradually up until he reached the bridge. So it's going very gradually. So I don't know, maybe something like this, very gradually up. All right. And it says it took him about an hour, so a decent amount of time. It says then he got to the top. And see, he took in the views for a few minutes. Now, if he took in the views, that means he's probably standing there. And if you've ever been to Natural Bridge, it's pretty flat once you get to the top. So we probably need to level off. Right? Notice his elevation hasn't changed. Time still marches on. He's standing there, but he's not going up. He's not going down. He's just standing around the top. He may even be walking around at the top, but his elevation's not changing. He's not going any higher up or any lower down. He's just staying. So let's make this a little bit bolder. So he gradually gets up. He looks around for a little bit. And then it says he decided to take the chairlift back down. And if you've ever been to Natural Bridge, they do have kind of like a ski lift, a chairlift that you can take up or down. In this case, it says he's going to go down. And it says it only took him 5 minutes. So notice here, it took him quite a bit of time to make to that elevation. But it says when he goes back down, it only takes him 5 minutes. So he's going to drop in elevation very, very quickly. So instead of drawing the elevation like this going down, notice that's about the same slope upwards. We need to draw this in such a way that will show that he's really, really dropped here. The eraser's not quite working as well as I'd hoped. So in this case, it says he dropped. I mean, he dropped it very, very quickly. And there we go. So a gradual trip up. He's going up, 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 walks up, gets to the top, spends some time looking around, gets on the chairlift, boom, back down to the parking lot. Again, not a very specific graph, but it gives a basic indication of what's happening. Guys and gals, that's what we're looking for. All right, let's try another one. This is a good one. I thought this would be fun to try and graph out. Again, most of these stories are made up, folks. I've made no attempts to make anything true in this case. So Miss Kevin, let's use her for an example. She decided that she would sell cars on weekends to earn extra money. All righty. The first weekend, unfortunately, she didn't sell any cars. And then the second weekend, she sold one car. She alternated not selling any cars and selling one car for the rest of the year. So one weekend she does, one weekend she doesn't. It goes back and forth. All right. Sketch a graph of Miss Kevin's sales over time. All right. And again, notice what we're measuring. Sales over time. All right. So let's get that on there. So time, in this case, since we're going over the course of perhaps, we won't track it over the whole year. Goodness gracious, we'll be here all day. Let's track it over, we'll say maybe weeks, just to give the reader an idea of the amount of time. Not that each one of these represents a week, but just to give them an idea. And then sales. In this case, number of cars. Okay, so here we are. So obviously, at the beginning, she doesn't sell anything, so we'll keep it flat. So that first weekend, she doesn't sell a car, right? Second weekend rolls around, and it says that she sold one car, all right? And remember, our marks here don't necessarily mean 1, 2, 3, 4, 10, 20, 20. They don't mean anything. They're just general scales out there to give us an idea. So I'm going to jump up a little bit to show that she's made a sale. Cool. She made a sale. And then the next weekend, it says she didn't sell anything, so it drops down immediately. Notice it can't be a gradual drop. She either did or she didn't. So keep going. Next weekend, she sells. Send it back up. She makes that same, notice it's the same level. One car here, right? And back down. And then the next weekend, she doesn't. And so obviously the rest of the year would continue in that pattern where she's sold nothing. Oh, she sold something. Oh, she sold nothing. Oh, she sold something. And back and forth. But again, we're getting just the basics of the graph. We are not spending our time focused on minute details and getting all the numbers just right. It's just the gradual feel of the data. All right. Now, one thing I do want to point out to you, because most of these graphs have been fairly basic and straightforward, it's super, super important that you know what you're measuring. So here's what we're going to do. I made up a story about a cat. It's here. And we're going to draw two different graphs for the exact same story. And I want you to see how different those graphs play out. All right, so let's read the story first, and then we'll look at what we're trying to measure. All right, our story. A cat was laying on the floor asleep. All right, so it's there sleeping. Let's see. She was startled when a squirrel tapped on the sliding glass door across the room. All right. Excited, the cat ran to the door. The squirrel immediately ran away. The cat sat at the door watching for a few moments. Then she walked back to her spot on the floor, sat down, and eventually went back to sleep. All right, so a very simple story. We're going to draw two different graphs for the exact same set of information. The first graph, we're going to sketch a graph of the cat's distance from her sleeping spot over time. All right. The second graph we're going to sketch a graph of the cat's speed over time. So let's do the first one. Notice we're measuring distance from the sleeping spot over time. So let's put time here. And I don't know, we won't designate a unit of measure in this case like we did weeks or minutes. We'll just say time for this case. And then notice here we're going to say distance from sleeping spot. All right, my cat has a definite spot on the floor that she likes to sleep. All right, so cool. There we are. So let's redo the situation. And we're looking at how far she's traveled from that spot on the floor. And again, we're giving us, our reader, just a general idea. So the cat was laying on the floor asleep. Cool. So let's give us a little bit of time here right at 0. Because she hasn't left yet. She's just laying there asleep. Okay. She was startled when a squirrel tapped on the sliding glass door. Excited, she runs to the door. So her distance from that spot needs to increase at a fairly quick rate. So maybe it looks something like that. All right, she's run away from the spot to the sliding glass door. The squirrel immediately runs away, okay? But the cat sits at the door watching for a few moments, all right? So her distance isn't going to change. She's going to maintain that same distance away from the door, all right? So she sits, all right, for a few moments, sits there and looks around. It then, notice, it says excited, she ran to the door, so we made that kind of steep. It says she walks back to her spot on the floor. So this needs to be a little bit more gradual coming down. Notice a little bit steeper going up, a little bit more gradual coming back. Because here she ran to the door, here she's walking away from the door. All right. And then eventually she sits down and goes back to sleep. All right. Now, if you're looking at that going, well, I don't know, these two slopes don't seem all that different. All right, well, if it doesn't, then here's what let's do. Okay, if you've read it and realized, you know what, I don't really like that, let's make this even steeper to show that she's really running. All right, well then let's change it. Let's make it more like this. All right, does that seem better to you? And again, that's why we're using a pencil, so we can make these changes. So she's asleep, gets startled, sees the squirrel, runs to the door, stops, looks out the window, and then saunters back, walks very gently back, and then sits back down, goes to sleep. Cool. That's one representation of this situation, measuring, notice, the distance from where she was sleeping over time. Let's draw a different graph. This graph, we're going to keep up with speed over time. Now notice this is different. Distance over time, for example, let's say we were measuring it in feet per second. Well, if distance is in feet, time measured in seconds, what this graph is actually showing us is the cat's speed. Not going fast, not going fast, going slow, not going fast, right? It's actually stopped. In this case, I'm measuring the cat's speed over time. If I'm measuring speed over time, what I'm actually measuring is something called acceleration. I'm seeing the change in speed. Notice this is distance over time, so I'm actually measuring speed with my graph. This is going to be speed over time, so I'm not really measuring speed. I'm measuring something called acceleration. How is the speed changing? Notice this is measuring how the distance is changing. We call it speed. This is acceleration. All right, so keep that straight. So let's look back at our situation. Cat's laying on the floor. So her speed is at 0. So those two parts of the graph seem to match, right? Not traveled away from her sleeping spot, not going any speed still. It then says that startled, she runs across the room. So her speed's going to go up, not straight up, but up. And then if you've ever seen a cat or anything else run, if they run to an object and stop, that means they had to speed up and do what? They had to slow down. Because if not, they're going to hit, say, the glass door and come to an immediate halt. So in this case, our cat speeds up to the door and then eventually has to slow it back down and comes to a stop, right? So runs to the door and then sits at the door. So in other words, her speed is at, whoop, if I can actually write, her speed then is back at 0, right, for that time that she's sitting at the door. And then it says she walks back to her spot. So her speed is going to gradually increase as she's walking, right? She might maintain that speed for a set period of time. She's going to slow back down, come to a stop, and now she's back at her sleeping spot. Take a look at our two graphs. These two graphs look extremely different. This one goes up, maintains, gradually down, stop. This one, level, up, down, level, gradually up, stays, comes down, level. Exact same situation, two different ways of measuring. Here we're looking at her speed. How fast did she go? Moved a lot of distance in a short period of time, moved quick. Didn't change her distance over a long period of time. Okay, she still traveled a decent distance over time, much slower than she did before. Here we're measuring speed. No speed, speeding up, slowing down, no speed. speeding up, maintaining that lower speed, slowing down, stopping. Same ideas, right? Same ideas, two different ways of viewing it, right? Same situation. So this is what we're going to be doing. Reading these situations, coming up with graphs, and guys and gals, we're just trying to get general gist, right? Please don't get too hung up in the minutia, the little details. We're just trying to get the overall general flow of how the situation plays out. But the biggest key to being successful is right here. Know what you're measuring. All right, for example, one last thing. Let's look at this one for a third time. All right, we'll just draw something kind of loose here. What if I asked you to draw my cat's elevation over time? In other words, how far up and down did she go? So for example, if she jumped on the sofa, that means she's gotten a little bit higher up, or she's jumped on the bed, maybe a little higher up, or if she jumps off the table, she's gotten lower. What would the elevation over time for this situation be? Well, notice the situation says she's on the floor, runs across the room, still on the floor, sits on the floor, watches the squirrel go away, walks back. She never leaves the floor. So another graph for this exact same situation, if I'm measuring elevation over time, would look like that. She never left the floor. Now, if she had to jump up to a window to see the squirrel, all right, well, maybe she's on the floor, jumps up, stays at the window, and then goes back down. But if she stays on the floor the whole time, we don't ever get that jump up. It just stays flat for the entire situation. So again, we got to know what we're measuring to know if what we're drawing makes sense, or if maybe we need to draw something else. All right, we'll spend some time in class looking at different situations. Make sure you bring a pencil with you. If you have any questions or concerns, please write those down on your notes. That way you'll remember them when we see each other in class. All right, have a good day, folks.